Hello, everybody. Welcome back to another lecture in which we're going to talk about complex numbers. So, why do we talk about complex numbers? Because they are deeply related to sine and cosine, which we choose as building blocks to our functions. So, we want to know sine and cosine in a deeper connection. So, we need to know complex numbers in a deeper level. So, how do we know them? Before anything else, let me tell you this: a complex number is a two-dimensional number. Yes, we have two-dimensional numbers. So when I say 5, it is one-dimensional. It is only 5. But complex numbers has real part and imaginary part. When I say 5 or 23.07, it's a real number. So it is actually a complex number with imaginary part being 0 because complex number set includes real number set. This is important. So a complex number has two dimensions, and those dimensions are real dimension and also the imaginary part. And whenever we want to denote, we want to show any complex number on the coordinate system, we need to use both axes, the x-axis and also the y-axis. How do we do it? It is quite easy. There are actually a couple of ways to denote a complex number, but let me show you how do we show a complex number on the coordinate system. So to do that, actually, I'm going to draw two basic lines to form a basic coordinate system. In the most general way, which is the rectangular way, we denote a complex number by just saying a plus jb. And a complex number is generally denoted by a capital Z. Let me put it in here. This is the capital Z. This is the denotion. And this is the extension of complex number A and JB. The part where you just have the number is called the real part. And the part where you also have the complex unit is called to be the imaginary part. So one thing important in here is that we have the definition of complex unit, which is the J right over in here. Let me actually take it on in here. J is the complex unit, and it is quite important. Normally, people who deal with math use an I to denote the complex unit. However, I am an instructor in electrical and electronics engineering area where we use the letter I to denote electrical current. That's why I'm going to go on with the letter J. This is important. This is something you should definitely note. So J is the complex unit. And J is equal to square root of minus 1. No matter how bad it looks, it is real and it is correct, because generally students tend to have the idea of square root not having anything negative in it. No, it's not true. It could also have something negative. Imagine you have a quadratic equation which has a discriminant of a negative value. What do you do then? I mean, if we were in high school, we would say there is no root to this equation. However, this is not true anymore since we are in university or college or whatever it is. We are at a deeper level of math. So we say now the root is a complex number because square root of minus 1 allows you to do lots of things. For instance, when j is equal to square root of minus 1, you could also say j squared is equal to minus 1, which is pretty good, right? Because square of something is negative. Oh, way. This is something different. What about j cubed? It is equal to minus j. What about j to 4? It is going to be equal to 1. This is important. And this particular pattern repeats itself because when you're looking for j to the 5, it's going to be again a j, which is square root of minus 1. Try it again. J to the 6 is going to be minus 1. J to the 7 is going to be minus j. J to the 8 is going to be 1. This is going to repeat itself in every four step. In every four, you're going to repeat this pattern. So why is it important? Let me tell you why it is important, but before that, actually, let us dive into the notions, the different ways to show a complex number. As I said, this is the first way. This is the rectangular way, by the way. It is called the rectangular way. But we also have another way called the polar form, which is pretty useful. And in order to explain the polar form, we're going to use the Cartesian coordinate system right here. As I told you, we have real and imaginary parts of a complex number, and when we want to show it on the coordinate system, we need to use both of the axes. So how do we do it? We treat x-axis as the real axis, and we treat y-axis as the imaginary one. So if you have a and b greater than 0, in this case, we can simply do something like this. A in here, be in here imaginary part and real part that are spotted on the coordinate system, and then we're going to connect these 2 points so that we would have a vector something like this. And this vector has a magnitude, definitely. Let's call that magnitude as r. Okay, and this vector also has an angle in between with the x-axis, or you could also say real axis, which is, let me show you with an orange color here. Let's say that this is theta. So basically, we could explain a complex number with a magnitude and also a phase angle. This is pretty important because a complex number is nothing but a vector since it has 2 dimensions. It has 2 dimensions, so two-dimensional vector it is. It is quite easy. So how do we do the conversion, by the way? If we have a plus gb, okay, we could also, let me just first show you this. A complex number can be denoted by a magnitude and also a phase angle. But how do we do the conversion from rectangular to polar or vice versa, polar to rectangular? How do we do it? It is actually quite easy, and every little secret is hidden in this particular triangle we have over there. So logically, whenever we have this r, we also can see the fact that this is the triangle we have, and this part is the length of A, and this part is the length of B. And here we have a 90 degrees of angle. That's where actually we can easily say that r square is equal to a square plus b square from basic calculus, and r is going to be equal to square root of a square plus b square. This is easy. This is quite easy. But what about the angle theta, which is a lot easier? Why? Because if you have the basic knowledge on trigonometry, you're going to see that the tangent of this theta, let me do it in here, tangent of this theta is going to be equal to b over a. So logically, if we take arctangent or inverse tangent of both sides, I mean, when I say arctangent and inverse tangent, I said it like they're two different things. No, they're the same thing. I mean, we just have two ways to call it. So arctangent of both sides, on the left side, we're going to left with the angle itself, which is theta. On the right side, we're going to have arctangent of b over a. So this is how we define theta and r, so that actually we can easily do the conversion from rectangular to polar and polar to rectangular. This information is really important. And I also want to show you something else, the projection of the vector we have over there. Let me show you. So first of all, we have a vector like this. It has a magnitude of r, and it also makes an angle theta with the x-axis, which is going to be something like this. So here we have the angle. Let me go back and draw it like this. Here we have an angle. So the projection of this particular vector to both y-axis and x-axis can easily be calculated through the value of theta. How so? Let me show you. The x-axis projection, let's call it as a, because we know that it is equal to a. And also the y-axis projection, let's call that as b. So simply, if you use the cosine value of the theta, you're going to have the value of a, which is the horizontal projection. If you use the sine value of theta, you're going to have b, which is the vertical projection. Let me do that in here. A is going to be equal to r times cosine theta, and b is going to be equal to r times sine theta. And these are details that are really important, which we are going to see later throughout this course. And by the way, these are pretty basic when it comes to electrical engineering, so you definitely need to know about them. But yes, we've talked a bit, we understood what a complex number is, and now we have the information needed to move on. And where are we going to move on, by the way? Euler's equation. Why? Euler's equation is something out of this world. Euler equation explains the relationship between a complex exponential and sine cosine. This is pretty important. This is gold right here. So first of all, let me put a title, Euler's equation. First, I'm just going to give you the general equation, and I'll talk about a bunch of facts, and then I will show you how to obtain Euler's equation, because now we are engineers. If you memorize something, you are a slave, because once you forgot it, you don't know nothing. You are a slave to that thing, whatever you have memorized. But if you know how to get things, then that particular thing is your slave. That particular thing you didn't memorize, but you have the knowledge of getting, is now your slave. This is important. So we gotta know how to obtain Euler's equation. If you're engineers, we should be able to do that. How are we gonna do it? So in every basic possible way, Euler's equation is something like this. Whenever you have e to j theta, and as you can see, we have an exponential, which is a complex exponential since we have the complex unit j, it is gonna be equal to cosine theta plus j sine theta. As you can see, it is in the form of a complex number, but how do we get there? Actually, we're going to use Taylor's and Maclaurin series for this, and it is quite easy. We're going to use the expansion of cosine, sine, and e to theta in here. Taylor's and Maclaurin's expansions. If you don't know about it, no need to worry, because at the end of the course, there will be a part entitled as there will be a section called additional material where you're going to see Taylor's and Maclaurin series and how to obtain them. But if you know them, that's good. Let's move on. So cosine theta has an expansion, or let's just not use theta, or let's use x, has an expansion something like this: 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus not plus, minus x to the 6 over 6 factorial. And I think you see the pattern here. It just moves on like this. Sin x has a similar pattern. Sin x is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and it goes on like this. What about e to the x? E to the x is a lot easier. 1 plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial plus x to the 4 over 4 factorial, and you see the pattern. It goes on like this. So how do we use it? Actually, Euler was genius because he thought, what happens if I replace that x with an ix? I mean complex unit times x. So we're just going to do a little conversion there. We're going to say we're going to replace x by jx. So when we do it, we're going to have e to jx, which is going to be equal to 1 plus jx plus, this part is important, jx squared over 2 factorial plus jx cubed over 3 factorial plus jx to the 4 over 4 factorial plus jx to 5 over 5 factorial plus, and I'm doing this one by one because I want to show you a magic, jx to 7 over 7 factorial. This is what we have. So logically, when we do a little conversion, because 1 plus jx, yes, those are cool, but what about this? This is basically, this part is j squared times x squared. J squared, we know already it is equal to minus 1. So right here, let's change the sign. This is going to be minus x squared over 2 factorial. What about the next one? The next one is j cubed, which means that it is equal to minus j. Therefore, here again, we're going to have a minus j times x cubed over 3 factorial. What about the next step? We have j to the 4, which is equal to 1. So logically, we have plus x to the 4 over 4 factorial. Let's move on. What about j to the 5? It is equal to j, only one j. So we're just going to say j x to the 5 over 5 factorial. That's great. Move on. What about j to the 6? It is going to be equal to minus 1. So that's why actually we're going to have a minus sign and we're going to say x to the 6 over 6. What about the next one? That's going to be minus j times x to the 7 over 7 factorial. By the way, this is also going to be a factorial. Since we have the expansion of e to the jx in such a fashion, we could do something, because we know for a fact complex numbers have real parts and imaginary parts. So we need to separate them. How do we do that? Let me actually do it in a simple way. I will have the purple pen right now, the purple highlight. So the things that I'm highlighting in purple are going to be real parts. See, this is the real part. This is also the real part. Real part and real part. And with the yellow, I will highlight the imaginary parts. So we're going to combine them actually. So I will say e to the jx is equal to the real part 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and it goes on like that. No need to calculate the whole thing. Plus, the imaginary part, that's why I'm putting a j in here. So first of all, I have an x plus, then, or no, not plus, but minus, x to the 3 over 3 factorial plus x to the 5 over 5 factorial, and finally it just goes on like that till the end. So what I'm noticing is this. This is the expansion of sine. Let me show you. And this is the expansion of cosine. So I can easily say that this is cosine x and this is sine x. Therefore, the result is this: a to the jx is equal to cosine x plus j times sine x. This is how we obtain Euler's equation. And why is it useful? Because it explains the relationship between a complex exponential and sine cosine. And more importantly, now we are able to express sine or cosine by only using complex exponential. Let me show you how. So since this is the equation, now we're going to use a little bit of information from the previous lecture where we talked about even and odd functions. So basically, whenever you have e to the jx, this is the expansion you are having. But what happens if I change that jx to minus jx? In that case, we're going to have something like this: cosine minus x plus j sine minus x. We know for a fact cosine is an even function, so cosine x and cosine minus x are the same thing. Therefore, we're going to have cosine x. However, sine minus x is not the same thing with sine x. Therefore, actually, we need to take that minus sign in the sine to the outside of the parentheses, because it's an odd function. Therefore, we're going to have something like this, which is pretty cool, by the way. And let's call this one as equation 2. And let's actually make this one equation 1. Let us also create another equation by multiplying the second equation by minus 1. In that case, we're going to have on the left side minus e to the minus jx. And on the right side, we're going to have minus cosine x plus j sine x. Incredible. This is the third equation. Now we're going to do basic math. What happens if I combine equation 1 and equation 2? It's going to be quite easy. On the left side, I'm going to have e to the jx plus e to the minus jx. And on the right side, I'm only having cosine. Why? Because these two will cancel each other out. That's why. So I'm going to have 2 cosine x, which is pretty useful because now I know the value of a cosine x by only using complex exponentials, e to jx plus e to minus jx over 2. This is the expansion of cosine by using complex exponentials. And we're going to do something pretty similar in sine. This time we're going to combine equation 2 and 3. And when we do that, this time on the left side, we're going to left with e to minus jx minus e to minus jx, which is going to be equal to, be careful, 2j times sine x. Sometimes students forget to put j over there. So 2j times sine x. So when we leave the sine alone, we're going to have sine x is equal to e to the minus jx minus e to the minus jx over j2. So this is the equation for sine. So now you understand the importance of Euler's equation, because thanks to it, we are now able to express sine and cosine in terms of an exponential. And how is it important anyways? Why is complex exponential this important? Let me tell you, sometimes we take integrals that are really hard to take, especially the ones where you have the square of a cosine or sine. It is really hard. But now with this help, actually, we know for a fact we can easily convert a sine or cosine into complex exponential, which is a lot easier to integrate. We know for a fact. And we will also see some parts in which actually the Fourier transform or series become a lot easier thanks to this particular equation or identity, whatever you prefer to call. So this is going to be the end of this lecture. And in the next lecture, we're going to talk about orthogonal functions. See you in that one.